Hi everybody and welcome. The music AI community has been taken by storm by a paper recently published by Google Research on text-to-music generation. Here you can see a tweet by Cambridge Choi, a great AI music researcher, who wrote, "Wow, this is bigger than ChatGPT to me. Google almost sold music generation, I'd say." In this video, I'm going to give you a breakdown of this paper titled MusicLM Generating Music from Text. I'll explain the architecture, the experiments that they've run, some of the limitations, and I share some of the thoughts that I have regarding this. And finally, I'll try to answer the question whether Google has actually solved a music generation for all of us. Let's go ahead and take a little bit of a step back from text to music generation and think about the wider context. So where does text to music generation come from? Well, it comes from text to image generation. So it branches out from there, from these ideas. So what is text to image generation? Well, I'm sure everyone subscribed to the Sound of AI YouTube channel is familiar with that. So these are models like DALL-E 2, like Midjourney, or Stable Diffusion, where you can pass in a prompt text like a cubist woman painted by Leonardo da Vinci, and the generative model generates an image for you based on your text prompt. Now, this idea has been extended to music as well, and now we have text-to-music generation, or TTM models. The sort of underlying idea is the same. You pass in a text prompt, and then a music generative system sort of understands the text and outputs an audio that hopefully will adhere to the text input. There are a lot of issues with text-to-music generation, many issues, but one which is major is that it is very difficult to describe music through words. The semantic of music isn't really clear, and the research lines on this are still very, very wide open. There's a lot of ambiguity and subjectivity indeed in describing music with words. Now let's take a look at some of the results of MusicLM, so this new Google system, text-to-music generation system. So here you have a demo page with a lot of music generated by the system. So we'll quickly take a look at some of this. So this one has this text entry, so the main soundtrack of an arcade game. It is fast-paced and upbeat, so on and so forth. Let's listen to this. Okay, yeah, so let's move on to the second. For example, a fusion of reggaeton and electronic dance music with a spacey, otherworldly sound, and then more information about it. Let's listen to this. So yeah, as you can hear, really interesting results. Now, there are other examples which are long generation. They have clips of up to 5 minutes worth of music. And then there are other modes that you can explore by yourself. But let's go back to the actual paper here. Okay, so text-to-music generation is by no means new, and recently, over the last couple of months, 3 months, there have been a lot of papers and systems released in this area. A couple of notable examples. So one is Riffusion, that uses stable diffusion, so diffusion models to generate audio via spectrograms. So there's a demo of Riffusion as well, so you can go to the Riffusion website and try it out for yourself. Mubert AI has a different approach to text to music. What they do is basically they use a transformer model to map text inputs onto their tags, or the tags that they use to generate music, and then they query the Mubert AI generative music API so that they can generate music that has those tags that are the closest to the text input. Okay, so many different approaches here. The one used by Google goes in a direction which I have to say which is quite different from what I've seen around. This is the architecture in a nutshell. There you go. Yeah, it's quite imposing and it can be overwhelming, but don't worry. We are going to just like break it down component by component for you. But the most important thing here to understand is that these type of systems just MusicLM, just like many other generative systems, not necessarily in music and audio, but also like in other domains, are becoming ever more complex, and they are becoming what I call matryoshka models, in the sense that they are not a straightforward self-contained model, but rather they rely on other models to do certain tasks, so that they embed models, which embed models, and so on and so forth hierarchically. What this means is that the overall architecture becomes ever more complex, and it's difficult to understand all the different parts, because I mean there's a lot of research and all of this is very cutting edge. This is also like a sort of like thing that I wanted to say as well. So in this video I'm going to give you a technical overview of how MusicLM works and how they've trained it and all of this. So there may be many things that you may not necessarily understand because you lack prior knowledge, so I'll try to break down these concepts at a high enough level so that at least you can get a glimpse or an intuition of that. Cool, let's move on. As I said, this architecture has or relies on different components that do different things. So here we have the main three protagonists of our story. The one is called SoundStream, the other one is W2V-BERT, and then we have MuLan. It turns out that W2V-BERT and MuLan work together in another system, again, deployed, or well, not necessarily deployed, but published by Google, that's called AudioLM. And it has been published earlier last year. The thing about AudioLM is that it basically does more or less what a MusicLM does, but it does it with speech and audio. It's more audio agnostic. It's not sort of like music specific. And so AudioLM is made up of W2V-BERT and MuLan. In a sense, we can think of MusicLM as SoundStream plus AudioLM, or if we look at different components as just SoundStream plus W2V-BERT plus MuLan plus the combination of this together. Let's take a look at each of these components and see what they do, and then we'll see how they sort of are combined together to arrive at those quite impressive audio results, music results that we've listened to earlier. Okay, so SoundStream. So what is SoundStream? Well, SoundStream is a neural audio codec. What does this mean? This is an audio compressor. So it is able to take a waveform and compress it at a lower bitrate. And the great thing about this neural audio codec is that it maintains a high reconstruction quality. So it's able to compress and decompress audio and maintain audio fidelity quite high, so up to 24 kilohertz. And SoundStream has been trained with residual vector quantization. Then we have the other part, which is W2V-BERT. And this is a BERT for audio. So I'm sure you are familiar with this transformer architecture called BERT, but this has been used for audio and it has been originally trained on speech. And this one takes care of semantic information. It has the capability of modeling long-term structure. Okay, and then we have MuLan, which is another system published by Google. And MuLan is a music text joint embedding, or it's a model that allows us to arrive or to use music text joint embedding. In other words, what this does, it links music with its descriptions in a free format. In a sort of like more formal way, what this does, it combines these two embeddings, which come from audio and text, into a joint embedding that is a single vector, basically, that has information both about audio and its textual information or description. We have, as I said, two embedding towers. So what does this mean? Well, it's basically two models that create embedding, one for audio and one for text. The embedding network for text is BERT pre-trained on text. And then for the audio embedding part, we have a simple ResNet 50 model trained on spectrograms. They train MuLan on pairs of music clips and their corresponding text annotation, and they use contrastive loss so that they can arrive at this cross-modal embeddings that have information about both text and the music. So why is this a very interesting model? Well, because now all of a sudden you can have embeddings that are sort of like connected for music and descriptions. So if you have a piece of music, then you can get the relative text description via this joint embedding and vice versa. And so this is a trick that they'll use here for the MusicLM model, and it works pretty well, as we'll see. Let's take a look at the training step. The first one is to extract tokens from input. So we extract three types of tokens. Acoustic tokens, which we represent with a capital A, and we extract them with SoundStream. So from the waveform, we extract these acoustic tokens. Then we have semantic tokens that are extracted with WTV-BERT. And finally, we have audio tokens, which are extracted with a MuLan. Okay, so now we have all of these tokens. So what do we do with them? Well, first of all, we're going to create a semantic model that predicts semantic tokens conditioned on MuLan audio tokens. The third step aims to predicting acoustic tokens that are the SoundStream tokens conditioned on both MuLan audio tokens and the semantic tokens. This may feel a little bit abstract, so we'll go back to the architecture and see all of these steps in action there. Okay, so we're back to the training architecture. Now, hopefully you should have a better understanding of the different moving parts. Let's take a look at the first step. Well, we input our audio, so our waveform, and then we extract all the different tokens with MuLan, with W2V-BERT and SoundStream. Now, you see here there are a couple of additional steps. So there's a residual vector quantizer and a k-means. These are used for post-processing really the embeddings that come out from MuLan and W2V-BERT, and their task is that of discretizing or quantizing basically like these embeddings. Okay, so now we move to step 2, which is the semantic modeling. So as you can see, we have the MuLan tokens, which we use for conditioning the training so that we can get a mapping for the semantic tokens starting from MuLan tokens. And then we have the third step, which is that of acoustic modeling. So now the acoustic model is conditioned on both MuLan audio tokens and semantic tokens that we've created with the semantic modeling. I'd like to give you a little bit more information about training. So each stage, so the semantic modeling and the acoustic modeling, are modeled auto-regressively as a sequence-to-sequence task using decoder-only transformers. This is a fancy way of saying that we have this problem solved as a sequence-to-sequence task, which basically means we input sequence of tokens and we generate sequence of tokens. And for doing that, we use a decoder transformer. And this doesn't come as a surprise because transformers work overwhelmingly well with sequence data. And all of this concepts and idea for MusicLM is sort of derived from NLP, where transformers are just the king architecture. In this sentence, we have a fancy word, which is autoregressively. So what's an autoregressive model? Well, I'm going to explain that by looking at the math for the semantic modeling and the acoustic modeling. So for the semantic model, what we try to do is we try to derive a probability distribution where we try to get the semantic tokens at time step t, and that depends on all of the semantic tokens at previous steps or time steps. So this is the concept of an autoregressive model. So the new token, the token at time t, depends on the previous tokens. An example of an autoregressive model, very famous one in the audio space, is WaveNet. Right. So in this probability distribution, not only we have the autoregressive part, but we also have the conditioning of the MuLan audio tokens. In other words, this probability distribution depends on the audio tokens as well. For the acoustic model, we have something very similar, but of course the variables are the sort of like quantities, factors are different. What we try to do is we try to understand or derive the probability distribution of the acoustic tokens or the SoundStream tokens. Specifically, when we want to derive the acoustic tokens at time t, these depend on the previous acoustic tokens at previous time steps, as well as on the semantic tokens and the MuLan audio tokens. Now you should have a solid understanding of the different parts or components of MusicLM and how they interact for training. Let's take a look at the inference part. Here's the inference architecture. It should be quite clear to understand how it works because you know the different components already via the training steps. Okay, the first step for running inference is to provide a text prompt. This is a music description like a hip-hop song with violin solo. We pass this text into the MuLan model and we get back text tokens, which we can pass to the semantic model in order to get the semantic tokens. Now that we have the semantic tokens as well as the MuLan tokens, what we can do is we can pass both of them to the acoustic model in order to get back the SoundStream acoustic tokens. Now we have the acoustic tokens, so we can use the decoder part of SoundStream in order to reconstruct audio starting from tokens so that we end up with a waveform. I'm sure you'll have a few questions. One that I want to address for sure is why do we have both an acoustic stage and a semantic stage? The answer is that they take care of two slightly different things. The acoustic model captures the fine-grained acoustic details, while the semantic model has the capability of making the overall long-term structure a little bit more coherent, and it improves also the adherence of the generated music to the initial text descriptions. There are a couple of tricks that researchers have used in order to arrive at this quantum leap in audio-based music generation. The first one is that they used a neural audio compressor, so SoundStream. So this made it possible to generate tokens instead of waveforms, or in other words, they lowered the dimensionality of waveforms, obtaining a lower dimensional sequences of tokens that describe them. Why is this important? Well, because waveforms are very highly dimensional and it's very difficult to model long-term structures when you're dealing with waveforms because of its high dimensionality. Using SoundStream is very clever because they reduced the dimensionality of a waveform onto a series of tokens that then they could use with relatively traditional models in NLP, so transformers. The second trick, which is super smart, is using MuLan, and this made it possible to use an audio dataset without text description. Why is that the case? Well, because MuLan is the one taking care of the text descriptions via its embeddings. So MusicLM offloads the text descriptions to MuLan. In this way, you can have huge data sets that have no descriptions, but it's not a problem because you can use them because MuLan is the one that provides textual information via its joint embeddings that can use an audio as a starting point, but then arrive at a joint embedding that has also information about text. Let's take a look at the experiments that researchers have run. The training data that they've used is different depending on the type of models that they've trained. First of all, for MuLan, they didn't train anything, they just used a frozen model. They used the free music archive dataset to train SoundStream and WTV birds. And for the auto-regressive model, so the acoustic model as well as the semantic model, they used 280,000 hours of music at 24 kilohertz. This is a massive amount of music. They trained these models with 30-second and 10-second audio clips. Once they've trained the models, they've run a good evaluation that has both quantitative and qualitative aspects. So for the quantitative part, they've used a few metrics that are standard use in text-to-music. For the qualitative parts, they used the judgment of experts, musicians. So for the evaluation, they created a new dataset that they've released. This is great news. It's called Music Caps, and it has text descriptions for 5.5 thousand music clips from the audio set dataset. And the results of the evaluation are quite compelling. MusicLM outperforms baseline models like Riffusion and Mubert AI. It has better audio fidelity as measured with the fresher audio distance, and it seems to have better adherence to text input. They've measured this with both quantitative metrics like the KL divergence, but also with expert-based evaluation. So all in all, it seems that MusicLM outperforms baseline models. Does this mean that Google has solved music generation? Well, I think we are very far from that. The model comes with a lot of limitations. First, the long-term structure isn't convincing. I've listened to the 5-minute clips and the long-term structure doesn't work. It feels like a random walk. And this is a particular problem of audio-based generative music systems. MusicLM doesn't solve that. I think the main problem here is that you have just a wild beast trained on a gazillion gigabytes of music, but without any real understanding of the underlying music or the concepts that make audio music. And for that, I think we have to integrate music theory, music knowledge via symbolic methods. So the other thing that I was a little bit upset about is that they didn't evaluate these longer clips, because I think like that is very, very important, because it's one thing to generate 5, 10, 30 seconds of music. It's another thing if you can maintain that level of quality throughout 5 minutes. Second limitation of the model is that the audio fidelity is okay, but it's not outstanding. It's not ready for production. I think that using SoundStream has been a great idea, and it has improved a lot over other models like Riffusion, for example, that use like spectrograms, but it still has a lot of issues. The audio quality is still not there. The third point that I think is quite problematic is that this type of models, text to music, have minimal creative control. You just like type your description and that's it. You get the output, you can't do anything about it. With diffusion-based models, you may have the possibility of doing some in-painting, which is quite cool, but even there, it's not really enough to change things in a music-aware manner. Just like saying, okay, so here I have this chord progression and I wanted to swap it for this other one, or I just want to correct this melodic line a little bit. You can't do that. You just like get the result as is. So because of all of these limitations, I think that a model like MusicLM could be a great product for TikTokers, people who want a lot of music, casual users, but it doesn't work for high-end creators who want to have more control over the music itself, and definitely not for musicians who want even more control over it. This is not a criticism of MusicLM, because I think like it's a fantastic piece of research. It is a sort of like wider perspective on what we want from our generative music models. Beyond the model limitations, I feel there are a bunch of issues with the research procedure. These problems are not unique to MusicLM, but more in general with sort of like this large generative system. Let me explain what I mean here. So first of all, this paper comes with no code and the model hasn't been released. This basically means that the results are not reproducible. One could argue that you could reconstruct like the model via reading the paper, well, but that's not really the case because a lot of things are just like omitted because of, like limitations and constraints and the length of the paper itself, I would argue, right? And in this case, I think we are at a point in time where it should be mandatory publishing code and also the model, hopefully, if you want to publish research in the AI, generative AI, music AI space. Of course, MusicLM hasn't been published. I don't know if they plan to publish it at a big conference, but I think it's a problem that a paper like this, which is fantastic, it's terrific, it's amazing research, but it's a problem that a paper like this gets accepted if the code, at least the code, isn't released. Another point that I want to make is that the farther we go with generative AI research and the more it seems that we are building Matryoshka models, and that's not a problem by itself. Well, it means that the entry barrier is sort of like higher because you have to understand a lot of things in order to put together like all the different pieces, but it's not that big of a deal by itself. But the problem is that many of these models are proprietary model. Like for example, here for MusicLM, you have MuLan, that is a proprietary Google model that has been trained on 44 million audio clips, music, text, audio clips connected together, which is just like something incredible. So in that respect, barrier to entry becomes really impossible because these models are not released and higher level models rely on lower level models that haven't been released, that are very difficult to train. So unless you are within one of these big companies, you can't really be competitive at doing generative music research using deep learning models. There are other ways, of course. And in that respect, I think the problem is that these smaller institutions can't really compete with the big guys. And the risk that I see is that we are headed towards an AI oligopoly where the likes of Google, OpenAI are going to be the only ones with enough data, resources, and not necessarily know-how, but actual proprietary models to bring the research forward. And this, for me, is a big, big red flag. I know this goes well beyond the scope of MusicLM itself, and it's something that applies to most of generative AI research nowadays, but it's something like that I think like we should think about, and probably I'll make a video about this. Well, by the way, let me know if you want me to reflect a little bit more on these points by leaving a comment in the description section below. If you want to continue this conversation, if you have doubts or ideas, you can share them in the Sound of AI Slack community, which is a friendly community with people interested in music AI. So it's free to join. I'll leave you the subscription, a link in the box below, so you can just go there and join it. I hope you've enjoyed this quite long video. If that's the case, leave a like, and as always, I'll see you next time. Take care for now.